Hello, welcome to the week 12 of problem solving sessions. Um, so this will be the last tutorial for this course. Yeah, and so far we saw classes such as NP, we saw the class P, and probably we might have talked about defined this class called EXP. Now the question is, yeah, and you also saw NP complete languages in here. So to draw the picture, you have EXP here, you have um, NP here, and you have P in here. The question is there anything inside P? Are there smaller classes that we can talk about? So okay, so in terms of yeah, in terms of time, uh, P allows you to take order n to the C time some polynomial in terms of the length of the input, where length of x is equal to n. Okay, and here you are allowed order 2 to the n amount of time. So okay, and here the only difference is that this is a non-deterministic machine, so you have non-deterministic Turing machine. Now all these three classes that were defined were with respect to the notion of time. The more time you allow, the more languages you might be able to accept. Okay, so are there any other classes sitting down here? So instead of order n to the c, if you restrict it to, let's say, if you only allow it linear amount of time, okay, then that would be a smaller class. So you're only allowed to read the input or take a decision within that. So that would be a much stronger class, and you can define any parameter that you would point in between. But the other um, the other important resource that we care about other than time is space. So instead of time, I can make all these three definitions by, I can talk about space here, I can talk about space here. Okay, so instead of order n to the c time, I'll allow you order n to the n to the c space. Okay, so that would be another class. So such languages where I allow um, n to the c space. So if I talk about space instead of time, then the corresponding class would be p space. Okay, and it does not make sense to talk about logarithmic amount of time. Okay, so I can't, if I say that there is a class A which is the set of all languages that can be decided within um, order log n amount of time. Okay, so why? So can someone tell why is this not a reasonable thing to do?
So that would mean that if the time itself is logarithmic, uh, so time could be logarithmic. It's not like that the time cannot be logarithmic. Like say in the case of the binary search, the time complexity is of the order of log n. That's fine.
Mm.
But probably the time of the order of log n does not make sense because even while reading entire input, we would be requiring at least linear amount of time. So we would be requiring sublinear amount of the time if we need not to visit every input at least once.
Yeah. So yeah. So if the length of the input is um, yeah, the length of the input is n, and you are only given order log an amount of time, then you are not even you're not even looking into the entire input, because yeah, by the time you take order log in many steps, you're already done, right? You'll never be able to read the other part of the input. So you don't even have time to look at the entire input, so it doesn't really make much sense to talk about these kind of um, yeah, languages. Okay, so however, instead of time, if I talk about space, then does it make sense?
Yes, yes, there it makes lots of sense, because if something is running in a space of the order of log n, would require the time of the order of 2 raised to the power log n. That becomes equals to n in that sense. Yeah. So
Yeah,
therefore, yeah.
yeah, that's correct. So if I define A to be the set of languages that take order log n space, then they are bound to run in the time taken by these machines will be at most n to the c, which is polynomial. Okay, so you are allowed polynomial time. So this sanity check is still there, that you do have enough time to look at the entire input and then make your decision. Okay, so these class of languages that run in order log n space in terms of where n is the input length are called is called L. So by this argument, so this argument is easy to see by looking at the number of configurations. So just look at the total number of configurations and observe that yeah, I mean, there can't be more than these many configurations if you're only allowed this much space. So it's a simple configuration counting argument. Okay, so yeah, so by that argument you get that L is inside P. We don't know whether they are equal or whether they are separate, similar to this question where we know that P is contained in NP. We don't know whether they are equal or not. Similar question, um, yeah, is open here. And then you can say that instead of um, talking about deterministic machine, what if I talk about a non-deterministic machine? Then is there a non-deterministic counterpart similar to P and NP? So indeed you can define that, and you get that so this is, yeah, so this is the non-deterministic counterpart of L, and by definition L is contained in an L, because if you just don't allow the non-determinism to be there, then this will be um, this is a trivially a non-deterministic Turing machine which doesn't use non-determinism. And by the similar argument you can actually show that NL is in P, but it's the same counting argument, but again we don't know whether they are equal or whether they are separate. Okay, and so this is the these are the two new classes with respect to space. And then again you can ask, what if I don't give you logarithmic space, I give you more space, so I give you order n to the c space, then such such class is called p space. Okay, and so any idea where should we place this? So in this diagram, where should p space lie?
So P space, I mean all NP problems are there in P space. So P space would be somewhere in between EXP and then NP.
Hmm.
But I have a doubt about this ESP thing actually. So when we say EXP stands for exponential,
Hmm.
so now exponential we have deterministic Turing machine and exponential,
Hmm.
and non-deterministic Turing machine and exponential. So
Um, wait, we are talking about EXP versus
so EXP stands for what? A deterministic Turing machine.
deterministic machine, which, yeah,
Then what about the complexity class wherein the non-deterministic Turing machine is taking exponential time?
yeah,
What that
so
class is?
yeah, NEXP, right? So it's a, yeah, you can have a non-deterministic counterpart for EXP, but it turns out that they are actually the same, as far as I know. Yeah, let me just quickly check this. Um, Yeah. Uh, oh, okay, okay, sure. So, sorry. Yeah, we currently don't know whether they are equal. The only thing you can say is that any XP must be, sorry. Uh, okay. So, any XP is here, yeah. We don't know whether they are equal. I mean, by definition, EXP is contained in any XP, but yeah, the quality is not known.
And then moreover, see when we see this entire hierarchy, what is this? The polynomial hierarchy. Then we have this sigma 2, we have pi 2, and sigma 3 and pi 3. And this, this exp class is there above all these classes. So how is that? I mean, the exp is so superior that this is there above all the sigma 2, pi 2, sigma 3, pi 3 in that hierarchy. So how is that possible? I mean,
Okay. So, okay. So, a complete language for the PH um, would be this TQBF, right? So you have a quantified Boolean formula phi, and you are checking instead of checking. So normally in NP you have whether there exists an x such that phi of x is equal to 1, right? TQBF instance would be whether there exists an x1 for all x2, there exists x3, and all kinds of alternations such that phi of x1 x2 up to xn is equal to 1, right? So if you can show that this is in exp, if you show that tqbf is in exp, that would imply that ph is in exp, right?
and what did you say in the beginning of this discussion that this TQBF is standard problem or what? What did you say something about the TQBF? You said something about the TQBF. The TQBF is standard problem or what?
uh, yeah, this is a, yeah, you can convert the ph instances into this, because ph is nothing but union of um, your sigma ip.
Yes, yes, yes.
So any problem can be thought of as these quantifiers, I mean, in
Correct.
terms of these quantifiers. So it's
Yes.
enough to show that pH is in EXP.
TQBF is in EXP.
Huh, sorry. Yeah, sorry. Yeah. Um, that TQBF is in EXP. And why is that? Because what is the brute force for doing this? You go through all 2 to the n um, assignments of x1 to xn. For each of them, um, yeah, for each of them, check whether these conditions hold. I mean, whether there is an x1 for which, uh, yeah, or I mean, just go through all the quantifiers. But in the worst case, all you're doing is you're going through all 2 to the n assignments. That's all. So, which is still just exponential.
Yes, yes. And moreover, this TQBF is a P space is P space
It's p
complete.
space complete. Yeah.
So and his P space is there inside EXP. So why don't we know the relationship in between the EXP and the NEXP then? I mean, where is the issue?
Mm, well, I mean, it's similar to why we don't know the relationship between P and NP.
Uh,
So,
because since every DTM, every NTM can be converted into the DTM, and this is only the issue of the time. Every NTM can be converted into the DTM in the worst case, in the worst exponential time. So now, if the DTM itself is taking exponential time, then exponential into exponential would mean what? Exponential only. So then, I mean, what are those problems and which are beyond EXP and are potentially there in NEXP? So are there some such problems?
which are, sorry, which are there in EXP but not in NEXP.
which are
Sorry.
not in exp and are potentially there in NEXP.
Okay, I mean, if we, okay, you mean potentially, right? I mean, as of now, we don't know whether there are such
Yes, yes,
languages. Otherwise, the classes would have been
yes,
separate, right?
yes, yes.
Um, yeah, but if you could separate EXP from NEXP, then you would have separated P from NP. So the following theorem, which is some kind of a padding argument, that if EXP is not contained in NEXP, um, then it would imply that, sorry, other way around. Mm, yeah, then P is not a proper subset of. Okay, basically, let me just. Yeah, so this is true. If you separate those two, then you would have this. But candidates for this is something I'm not. Yeah, I don't know if there are good candidates here.
Okay, okay. But then I have understood by and large this thing. Yeah, thanks. Thanks.
Yeah. Okay. So where does this class P space belong? It would be, so by a similar configuration counting argument. If you have, so earlier you had logarithmic space, you have, which corresponds to 2 to the order log n time, which is nothing but poly time. Similarly, here you would have 2 to the um, k n to the c time, which is nothing but exp. So this is some exponential amount of time. Okay, therefore p space is here. Okay, and um, yeah, and it's also easy to see that np is contained in p space because um, sat uh, can be, I mean, sat is inside p space, so therefore every language inside np can be solved in polyspace. It can also be seen by the observation that sat is nothing but a special instance of tqbf, where you don't have these quantifiers, you only have one quantifier. And since this is in p space, by default this satisfiability is also in p space. Okay, so yeah, are there any questions about these complexity classes?
PSPACE each union over all polynomial pace. So, what is the meaning about the PSPACE related to these things?
Relative to which, relative to what?
NP or NP an exponential time pace complexity relations. Can you given some example?
Some example of, um, sorry, I didn't get your question exactly.
Union over all polynomial pace. Can you simplify it? Why? What is the union actually? Actually, what set are uses here?
um, okay, so okay, so okay, just to give a um, contrast. Okay, so p was defined as union of d time um, n to the c for um, hmm, okay, and how do you define p space? This is the union of d space n to the c, right? So okay, so you want to see an example of um,
This phase. So, what is this phase, ma'am?
So you see, I mean, are you familiar with D time?
Deterministic.
Yeah, so D here stands for deterministic. So this is the set of languages accepted by deterministic Turing machine in n to the c time, and D space would be the same thing. This is the set of languages accepted by deterministic Turing machines in n to the c space. Okay, so I mean, so this is basically you're allowed um, order n space, you're allowed order n square space, you're allowed n cube, and so on. Anything power of a constant, right? So
So actually, many measurement is memory used by tuning machine, but they are different deterministic and how they are defined.
um, I did not understand your question. Sorry. Can you please repeat?
These piece phase and these phase deterministic phase. So both measure memory used by a tuning machine, but they differ in determinism and how they are defined.
Okay, so P space is, um, I mean, we call this class as P space. D space is just a notation. Okay, so I mean, it's just used for defining what P space is. But when you want to talk about languages that take polynomial amount of space, you will always say P space, because um, I mean, we defined it to be that class, whereas D space is just a notation. So when someone says, um, for example, that there's a machine M, which I mean, I'm not even describing what the machine does, but if this machine runs in n square space, okay, then this machine M is in D space of n square, and therefore by definition of P space there is it is therefore contained in the union, because in particular it is in D space of n square. So therefore you will now say that M is in the class P space, but you don't have classes called D space of n square or something. You'll have to name it something, because at the moment it's just a notation. That's all.
Okay, okay. If I go through some advanced book and I have read carefully, then the articles, then I will understand. Okay, thank you.
Okay, okay. Okay, yeah. Any other questions? Okay. So based on the discussions, which of the following are true? Or okay, by true we mean something that's known to be true, because some of these things we may not even, yeah, we don't know, and we may not know answers to some of these at the moment.
So B is true because L is a subset of NL, and then NL is a subset of P, and P is a subset of NP. So therefore L is a subset of NP.
Yeah.
And because of the similar regions, so this P is a subset of the P space as well. Whatever we can do in the polynomial time, clearly we can do in the polynomial space as well. And this P space is a subset of the EXP is also fine. So except A, remaining three options are correct.
Yeah. So So let's look at B. So as we saw, if you have something that takes logarithmic amount of space, it will take 2 to the log n amount of time at most, which is nothing but order n to the c time. Therefore, L is contained in P, which is by default contained in NP. So this is true. And by the same argument, D is also true. Instead of log n here, if you just put n to the c, you get that P space is in EXP. For for this, P is contained in P space. If P runs in order n to the c time, then how many cells will it touch on the Turing machine? Okay, it keeps on moving back and forth, and let's say it never moves back, it just keeps whatever it does. If it keeps on moving always to the right, it would have touched at most n to the c or order n to the c cells, because it simply did not have time to go forward. Even if it just kept moving in the same direction, it will only have this much time. So therefore, whatever it does is always contained within this space. Okay, so it can touch at most order n to the c space as well. Therefore, P is contained in P space. And all these most of these arguments generalize, they are not restricted to P. Instead of n to the c, if I say um, n to the log n or something, same argument will follow. So such classes are called quasi polynomial, where you have order n to the log n amount of times, and then the same argument will apply if you have. So basically, all I'm trying to say is you can replace this with any semantically correct number, and the same argument just follows.
Quasi polynomial or quasi non polynomial? Quasi NP.
No,
Because at
it's
the
quasi
end,
polynomial if you allow a deterministic Turing machine to run in at most order n to the log n time, that's QP. But if you take a non-deterministic machine, that would be QNP.
QNP.
So this P or NP is just a question of what machine you are using.
Yes. Because for P, this has to be of the order of n raised to the power C. There is no variable as such. The
Right.
variable thing appears only when uh, oh, I see. All right, fine. Yeah. Thanks.
So C is also correct, and A is something we don't know yet. Yeah.
Actually, P subset of P pace, each polynomial time uses at most polynomial pace. It means, and P pace subset of exp time means a polynomial pace machine has it at most exponential configuration, and so that is the assumption. My is it true,
Assumption.
or
No, it's not the assumption. So
okay, that is the idea. So uh, that is my thought process. So it is correct or wrong?
that is correct. So if you have polynomial amount of space, you can have exponential, at most exponential number of configurations. Therefore, the machine runs at most exponential in an exponential amount of time. Yeah. Okay. Yeah. Any other questions?
Ma'am, why not possible NP subset of L,
NP is subset
or
of L. Okay.
yes, yes.
So yeah. So what that would mean is that mm yeah. So okay. So first observe that P is contained in NP, right? So showing that P is a um, subset of L is, I mean, if there is a difficulty in showing that P is a subset of L, then showing that a larger set is a subset of L is even harder, right? So,
Yes, yes,
yeah.
yes.
So, I'll just then explain why this is not easy to see, or why we don't know, okay, that whether they are P is contained in L or not. So, if your machine runs in polynomial amount of time, okay, then like we said earlier, right, it is possible that maybe it does need um, does need more space to come up with the answer. Okay, so okay, one example would be um, let's say, okay, what is a good example? Okay, maybe just take reachability problem. So you have reachability where you are given an input as the input is a graph G and S and T variables, and say yes if there is S to T path in G and no otherwise. Okay, so what is a trivial algorithm to do this? You would do a BFS or a DFS. um, okay, so you look at your graph G, start at vertex S, and maybe go for all possible neighbors of S. Okay, and then you go for their neighbors and keep on doing this. If you reach T at some point, then you will say that there is an S to T path. Otherwise, what will happen is, after some amount of steps, you would have repeated a vertex, in which case you have a cycle, and if there is a cycle, then you are just going over and over across that path. There's no, you can't escape that loop and then never see a T. So you will discard such cycles, and at the end, when you terminate, if you have never seen T, then you will say that there is no S to T path. That's the algorithm, and this runs in polynomial amount of time. But more importantly, what is the space for required for it? So this is one language which is in P, but what is the space required by this algorithm? Because what happens is, if I let's say do a BFS, then I need to store all the neighbors of S, and then what I'll do is, the amount of memory will first store the first neighbors of um, so these many neighbors of S. Okay, let me just call gamma of S. These are the neighbors of S. Now what you will do is, for each of them, you will further explore their neighbors. So this is going to expand further, and let's say maybe you did not find anything, you terminate this, so you can reuse this part of it. But the the other guy will also expand. So at any point of time, it could so happen that there are like n by 2 neighbors at the same time. Okay, so it's not clear um, how I'll be able to reuse the space so that I maintain only order log n bits at a time. Okay, we are not saying that it's not possible, but it's not intuitive, because the natural algorithms that come to mind, like BFS, or even if you do some clever strategy, um, we always hit this block that you are actually using more space than logarithmic amount of space. So yeah, it's just that we don't know yet whether such whether it is even true in the first place. But yeah, but that's a block. Whatever problems we know, whatever strategies we know, they've yeah, always ended up using more than logarithmic space. Does that answer your question?
Yes, yes, yes. It makes some sense. So to clear, and it is a good to uh, follow.
Okay, okay, good. Any other questions? Okay. So, okay. Okay, so let's go over some closure properties. So, just to recall, you have this. We had this class P, and you know that P is closed under union because if you have um, m1, m2 which run in polynomial time, what you'll do is run both of them. Run m1, run m2. If m1 accepts or m2 accepts, then you are going to accept. If this is what your new machine does, then what is the time of this machine? This one takes n to the c time, this one takes n to the c time. Therefore, overall the machine takes polynomial amount of time, and you have your new machine for union. Similar thing you can do for intersection. Instead of or, you just make it an and, that will work. Yeah, and complement also works. You just run the machine. If the machine accepts, you reject. If it rejects, you accept. Same thing. Okay, so these are some of the properties you know about P. Um, so what can you say about, let's say, union for P space? We have two P space machines. Can you can you accept the union of the two languages in P space?
Question is not clear. What did you ask?
So basically, is P space complete, sorry, closed under union? So we are looking at closure properties. If you have a machine, or let's say language L1 which is in P space, and L2 is in P space, then is L1 union L2 in P space?
That's fine. That's fine. That can be that's fine. I mean, this is like proving, say, if L1 is recursive, L2 is recursive, so the union of L1 and L2 would also be recursive, kind of the thing. Because if a language is P space, then the language is decidable first. I mean, because for these complexity classes, the problem has to be decidable first. So this is fine. This is true. True in the sense that if L1 is, so there exists a machine M and which decides L1 in the polynomial space, and then there is a machine M2 which decides L2 in the, again, in the polynomial space. So for the union thing, what I can do, that yeah, so that I pass this L1, the instance of L1 in and L2 parallelly to both the machines, uh, and will that solve the problem? So if I pass, not, if not parallelly, then what can I do? I pass the, I mean, instance to the machine M1 first. Is if M1 says yes, then let us, I mean, it's okay, done. If M1 says no, then this will trigger the action of the machine M2. So using this strategy, we can show the closeness under union, the closeness under intersection as well. I mean, because by making a tiny modification here and there, and similarly for the complement as well. But now, as far as the Kleene closure is concerned, so in the case of the Kleene closure, what is to be shown, that if L1 is in the P space, then does this mean that the Kleene closure of L1 would also be P space? So I mean, L1 can be repeated any number of the times, and N1 can be repeated. So this union would be the infinite union. And if it is a finite union, then probably something can be said, but the trouble will occur because of the infinite union thing, I guess. So I'm not sure.
Yeah, exactly. So Um, yeah. So it's the same machine that, I mean, the same idea that you'll do for union intersection as well as complement. You run M1, run M2, and then decide um, this or use or in case of union and in case of intersection. And the analysis is the same, that M1 runs in P space. So this M1 would run in some order n to the C space. Okay. And what you can actually do is you can reuse the space, but it doesn't even matter. We're not being conservative here, and let's just forget about it. Use some new space, and this also is some order n to the C. But if you sum it up, this whole thing is still order n to the C. So the space that we ended up using is still polynomial. Okay, so this is yeah. So the analysis goes through for union, for intersection, and also for complement. All three go through. The trickier case is the clean star. Okay, so what does that mean? If L1 is in P space, is it true that L1 star is in P space? Okay, and L1 star is um, okay, is there a simpler way of writing this? Okay, basically the input to this would be, if X is the input, X is in L1 star, if and only if there exists a partition. So X can be written as X1, X2, X3 up to some Xk. There exists X1, X2 up to Xk such that X is a composition of a concatenation of all of these, and for all xi is in L1. Okay, so what that means is there is some way to break X such that each of these chunks is individually accepted by L are in the language L1. So this is basically some, take a lot of strings from L1, concatenate them, all of those strings will belong to L1 star. Okay, so yeah, as Goel pointed out, if you are doing this business, so you are doing this n to the C, um, yeah, uh, sort of chunks like we did earlier. If you do this sort of a thing polynomial number of times, then n to the C times n to the K will still be some polynomial. But what if this number of chunks is very large? Okay, so I mean the point is that that cannot really happen, because what is your input to L1 star? Input to L1 star is X. Okay, and um, yeah, and what is the length of X? Length of X is at most n. uh, Sorry, length of X is n. So how many of these chunks can be there? What I mean, this K cannot be n square or something, right? Because each xi is of length at least 1, so this K is at most n. There cannot be n square n cube chunks. Okay, so for each of them there are at most n of these chunks, and for each of them you have to run an L1 machine. So what you will do is, for x1 you check if x1 is in L. This takes order n to the C space. For x2 you check if x2 is in L1. Keep on doing this for all of them. There are at most n many of them. Each of them takes order n to the C time. Totally it takes n times order n to the C, which is still polynomial amount of space. So the worry that we had was that if there are so many chunks, then we might actually be blowing up space, but that does not happen because of this fact that you are running in terms of the input size. So the partitions cannot be large.
This is not clear actually. So if X is the element of the Kleene closure of L1, then X cleaning closure of L1 would be L1 or L1 square or L1 cube and so on. Is this? And so therefore if X is the element of the cleaning closure of L1, then X may belong to L1 itself or X may belong to the L1 square and then so on. So from where this concept of dividing X into the multiple chunks arises?
Yeah, so okay. So if x is in L1 star, then x is in union of um, either x is in L1 or x is in L1 square or x is in L1 cube and so on. That's your point, right? It's in one of these.
Yes, yes.
Yeah. So um, if I mean if we are talking about just L1, then this is trivially easy to check. You just run your PSPACE machine. If you want to check for L1 square, then that means x can be partitioned into two, say x1 and x2, such that x1 is also in L1 and x2 is also in L2, is also in L1, right?
Right, right, right. Yes,
So,
yes.
yeah. So then what you'll do is you'll guess where this, not really guess, but go through all possibilities. Maybe assume it's here and check, or it's here and check. There are just n many possibilities here to check. And if any of them works out, then we are done. And you keep on doing this. So here you check for three partitions. So my point was that you don't really go infinitely long here. So you don't need to worry about a lot of partitions being there, because you only need to check till L1 to the n, where n is the length of x.
Yes,
So therefore you're still in polyspace.
correct, correct. So therefore, does this mean that P space is closed under the clinic closure as well?
Yes, yeah. So that means we have just proved that p space is contained in, uh, is closed under L1, under clean closure. Yeah. So yeah, so that will account to, maybe I'm not writing all the steps here, but you'll have to go for all partitions. So assume that first partition could be anywhere from index 2 to n. The second partition could be, maybe the first partition happens at I, which could be between 2 to n. Second partition could be between I1 to n. Third partition could be I2 to n, and so on. And yeah, um, so there are only many, polynomially many partitions to check.
Yes, yes. And moreover, the space can be reused, so we can try all possible combinations within the limited space only.
Yeah, yeah. Let me just write for the sake of completeness. And each check is in p space. So overall, this is p space. So what we've concluded is that if L1 is in p space, then L1 star is in p space. Okay, but yeah, if you look at it closely, um, can you generalize this argument for um, time? You know that. So yeah, you know that p space is complete. Sorry, is closed under all of these operations. And earlier we saw that by same argument, the class P is closed under union, intersection, and complement. Now, what can you say about clean star for P?
So for the cleaning closure for P, I mean, this time, since I mean, in the context of the time will, I mean, you need will explode. So therefore, the need not to be closed under the continuous star.
Hmm. Yeah, so the same argument will not work for time, because here you can, yeah, here you can reuse the same space, um, but um, yeah, but you can't reuse time. So it's possible that you might exceed polynomial time, but I think there's a DP argument to this. Um, as far as I
We can decide whether a string w is in L star using the dynamic programming. So try all possible split of w. Check
hmm,
each substring using the polynomial time decider for L. So number of split in polynomial time. So total time remain polynomial.
yeah, yeah. So yeah, there's a way to come up with a DP for it, which is, yeah, I think same as what you are saying, and using that you can actually show the closure under clean star operation. But yeah, we'll not do that, but it's a good exercise to try. Okay, but yeah, are there, huh?
But then we do not often, I mean, hear the closure properties of the complexity classes. Like for the first time, I saw the closeness of the p-space complexity classes. Like I never saw the questions within the closure properties of the NP or L or NL or the other complexity classes have been examined. Why
Yeah,
is it?
but these are actually useful, in the sense that, I mean, if you're I mean, a lot of problems involving fundamental complexity theory often use these properties. For example, closure of BPP, etc., is something that, I mean, is very frequently used when you are, I mean, working on problems. So, um, I mean, see, one small way to see the usefulness would be that if you are trying to separate two classes A and B, and you know that one of them is closed under some operation and the other is not, then you already know that the classes can't be the same. I mean, they can't coincide.
Yeah, yeah.
Yeah. So I mean, therefore, I mean, it's like a nice check to make when you are trying to separate classes. That is one direct use, but other than that, also they do come useful. Like, yeah, let's say you want to solve some problem, and you'll actually end up using some other machinery by converting it into some other problem, and now when you want to translate that back, you might end up asking that, okay, I'm actually solving for some function of uh, inputs over that language. Now when I go back, is the complexity, I mean, whether you're still within that complexity and so on. So that is
Yes, yes, yes. I understood. Yeah. Thanks. Thanks.
okay. Okay. Okay, so you might recall this language of emptiness checking for DFA. You are given a DFA, and you want to check whether the language accepted by M is empty. So you want to show that EDFA is NL complete. Now, as earlier, it's same as the definition for NP completeness. If you want to show that L is NL complete, um, first, L is in NL, that's the membership checking, And second, L is hard for NL in the sense for every language A in NL, A reduces to L. Sorry, okay. I think, yeah, I should not use L here because we already have a complexity class that is called L, so it can be confusing. Maybe I'll call this B. So we are talking about a language B, not the class L. Okay. A reduces to B. And yeah, I mean, as we have been stressing upon throughout the course, whenever you talk about reduction, you there are two parameters. What is the complexity of the reduction? So in this case, we are allowing the reduction to happen in log space. Earlier, the reductions that you had for NP, so just to contrast, you say L is NP complete if and only if B is in NP for all A in NP, A reduces to B, but here you had complexity class P, whereas here you have L. So it's always something potentially smaller than the class that you are concerned about. So if you're talking about NP completeness, the class involved here is something inside NP, which is P in this case. Whereas if you're talking about NL completeness now, the underlying reduction is something that's inside NL. So for example, L here. Okay. And yeah, it's a many one reduction.
Ma'am, ln and lp are same.
Um, what and what? Sorry.
Ln, nl, np complete are same.
NP complete and NL.
Nl complete.
No, they are not the same, right? Because for a language to be NP complete, it must first be in NL. Okay, and for a language to be NP complete, it must first be in NP. We don't even know whether every language in NP is in NL.
Okay, okay.
So now, to show this NL hardness, we can take the help of that ST problem, source to target, that reachability problem. And reduction can be shown like, so reachability in the sense that EDFA. So this, uh, I mean, M is an example. M is an instance of, or M belongs to EDFA. If we cannot traverse from the initial state to the final state. So if we cannot traverse, so initial state here becomes S and the final state here becomes T.
Yeah.
So whenever the ST problem instance says yes, that would be a no for this EDFA. So therefore, ST problem can be reduced into the EDFA. But I'm struggling with proving that this EDFA is an element of NL, because here we do not have uh, polytime verification equivalence something. So how to show that this EDFA belongs to the NL, except that I can decide this in the logarithmic space by some non-deterministic Turing machine. But how can this be done? So yeah.
Okay. Yeah. So yeah, we will go back to our reachability problem, which I'll call reach. Maybe I'll just copy that. Yeah. Okay. So this is the reachability problem that we defined earlier. Given a graph G and two vertices S and T, check if there's an S to T path. Okay. So what we know about okay. So first of all, let us show that reachability is in NL. Okay. So how do you show? So you want to come up with a non-deterministic machine, which um, yeah, I mean, which tells you whether it's a yes instance in logarithmic amount of space. So um, yeah, I mean, first of all, how do you, let's say, let's do a simpler thing. First, let us show that how do you show that reachability is in NP? How would you show this? Let's ask a simpler question.
So if you give me the certificate, then I can verify the certificate in the polynomial time that whether I can traverse from S to T or not.
Yeah. So what is the certificate?
Certificate would be the sequence of the vertices starting from S and till T.
Yeah. So go from, sorry. Okay. Yeah. So the certificate is you guess the set of vertices, let's say u1, u2, and so on, finally up to t. And what you are basically doing is you are checking whether in the graph there is an edge from S to u1, whether there is u1 to u2 edge, and keep on checking for each of these. Eventually, you should go to t. That's the that was the certificate, and it's a polynomial size certificate because there can be at most n vertices here. Okay, so now what you want to do is you want to say that, and yeah, of course the check is also a polynomial check. Okay, so now what you want to do is you want to say that in order for this um, argument to work, you want to you want to say that the size of the certificate is logarithmic. That's what you want to say. So if we could show that the size of the certificate is logarithmic, then we are done. Because yeah, I mean that is what it means for for the membership in NL, that you have a certificate of size logarithmic and you can verify it in that L space. Okay, so how will you do this now?
So
So
I can keep the counters instead of storing, like let's say S to whichever vertex and whichever state I am reaching to from the starting. I will just keep that counter value, and to store the counter, I would be requiring logarithmic space.
yeah, so you don't need this entire certificate upfront. I don't need to tell you this whole thing. Instead, what I'll do is when you are at S, okay, you are just storing where you are. So in the beginning, you are, so keep track of current vertex. Okay, so how much space do I need to keep track of vertices? There are n vertices. If you encode it in binary, you need order log n space for this. Okay, then you want to know where to go. Okay, there are so many neighbors, which one to take? That's the non-deterministic choice that you are making. So non-deterministically you will choose the neighbor u1. So, or okay, I mean you're not really choosing a neighbor, but just you are just guessing another vertex. Guess a vertex v in V. Third thing you're going to do is check if UV is actually an edge. So this is something that can be done in order one. If you have the graph that's given to you as an adjacency matrix, then you're just checking an entry u comma with entry. Okay. And by the way, this V also takes order log n space because it's an encoding of one among n vertices. So this also takes another log n space. And yeah, you might want to keep a counter. um, yeah, and after this point you maybe increment counter. Sorry. um, yeah, and repeat until counter is um, yeah, I mean basically just make sure that you have not yeah, I mean I didn't write n in binary but the binary of n. Yeah, so you don't want to go more than n times, because at that point you would have already been in a cycle, and if you still did not see t by then you are just done. So um, yeah, and if okay, maybe there's just one, sorry, sorry, increment the counter. If v is equal to t, then accept, otherwise you're going to repeat. So at any point of time if you do indeed see a t, that means there is um, yeah, there is an s to t path. Otherwise you are just going to repeat until you have um, seen all the vertices. If you have seen all the vertices, then you are going to reject. Okay, so yeah, so the whole point of this um, um, shrinking of the size of the certificate was that you don't need to know this entire thing all at once. What you do is you do it on the fly. From S you just go and look for the next neighbor. When you are at the next neighbor, you forget about everything that was there. From you just look for the next neighbor and keep on doing this. So you don't need to remember all of it at any point of time. You are just remembering two vertices. So this is the first vertex u, the second vertex v, and each of them just take order log n amount of space to be remembered, and there's a counter which is again which takes order log n amount of space. So all together this entire algorithm works in order log n space. So not only that the certificate is small, but also the check can be done in logarithmic amount of space. So therefore you have that reachability is in n. Is this okay? uh,
Basically, we are checking whether a DFA has no accepting string. That is whether no path exists from the start state to any accepting text. So may build the DFA as a directed graph and states transition and accepting state reachability check. And is there a path from start state to any final state? This is directed reachability problem.
hmm.
So that is why we reachability in ln, that is I can say that reachability is in unl, so non reachability in is also in a ln. So we prove that uh, an edfa belongs to nl.
Correct. Yeah. So um, yeah, so in order to yeah, check if there is, this is same as check if there is a path from the start state s to any of the final states, to any final state f in the set of final states. So that means this is nothing but, so if you view the DFA as a graph, so this is the start state, then you have several transitions. You forget about the labels essentially, right? You just don't even look at the edge labels, you just look at it as a graph, forget the labels. And Yeah, eventually you just want to check whether there is a path from S to any of the final states. So what you will do in this case? Uh, yeah.
Le-
Yeah, go on.
So, I mean, uh, what was your question? That how to?
Yeah. So you want to check whether there's a path from S to to one of the final states.
Yes, so I will call this ST problem. I mean, from the starting state to the final state.
Yeah. So there could be many final states, right? So
But then same space can be reused, isn't it?
exactly. Yeah, that's what I'm asking. So first, so let's say F1 to Fk, this is the set of final states. What you do is first you check whether there is a S to F1 path. If there is, then you accept. Otherwise, you check if there is an S to F2 path and so on. Basically, this can be done in um, this can be done in NL, but yeah, you can reuse the same space again. The second time you use that same space, this is in NL and so on. So uh, yeah, so the point is that if the space were not reusable, then this is a problem, right? Because this could be potentially many. So but yeah, I mean that's not an issue for us because of the reusability of space, and therefore as you mentioned, so the this is nothing but multiple instances of reachability problem, which is still in is in NL. So this part is fine. And
What about the reduction in the logarithmic space?
yeah, so you are not so you are given this DFA and sorry EDFA, and you want an instance for each. Okay, so what you do is you give it the same graph. Don't just forget the edge labels, whether it says a 1 or 0, just forget about that and give it the same graph as it is. And you need G comma U comma G comma S comma T. So what is S for you? S is the start state, whatever is the vertex, and T for us is hmm okay. So yeah, here you can't give multiple states to it as input. So what you will do is yeah, so okay, so do you see the issue with T?
No, no, I could not
So
obtain.
there can be multiple final states, right? Correct.
Yes.
So reach should accept, you want to check whether there is a path to at least one of them, but T is nothing but T is just one state, one vertex. How do you encode all of this information within that one state?
So, but then, I mean, there is a strategy that multiple final states can be merged into the single final state. That
Yeah,
will
yeah, exactly. So you will have to do that. So you yeah, so you know that if a DFA has multiple final states, there is an equivalent DFA with a single final state. So what you do is make all of them, make all the F1, F2, F3, make them normal states and add a new state F, which has oh sorry. hmm okay, how do you do this without using epsilon transitions and then converting it to
so even if, yeah, so there is no other way except except including epsilon moves to merge multiple final states into the single final state. But then this DFA will get converted into the NFA. That's fine. That's fine. So because the language accepted by the DFA is same as the NFA, so therefore if DFA is empty, then the NFA would also be empty.
Yeah, okay. That yeah, yeah. Even if you think of these as epsilon moves, it shouldn't matter because you are just checking whether some input reaches F. Yeah. So T for you is um, yeah. So the accept state T is nothing but F, which is the new state which yeah, where all of these final states go to. Okay, and now this entire reduction was done in log space because what you did is you passed the entire instance as it is by forgetting the edge labelings and the final states. You don't remember that. You just draw a new edge to final state from all of these old final states, and S is nothing but your start vertex, T is nothing but the new final vertex, each of which take logarithmic. These are nothing but order log n space. So the entire thing was in L. And now that you have a reduction from EDFA to L, and you know that reach is NL complete, so NL complete. So okay, I'm sorry. I think sorry, we did the other way around. No, we need to show that sorry, this reduction was not correct. You need to show that reach reduces to EDFA. If you could show this, um, then you would conclude that this would imply together that EDFA is NL complete. Right, so you take the hard problem and you reduce it to the problem that you want to show is NL complete. So what will you do? You want to actually show the other way around.
Yes, that's fine. That's fine. So, instance of the ST reachability can be reduced into what? Into the emptiness of the TFA. So, how to carry out this transformation in the logarithmic space? That is the problem. Logic seems clear that if I can make from move from S to T, then the EDFA is not empty. I mean, the EDFA is the language is not empty. But how to carry out this transformation in the logarithmic space?
Yeah, so my concern, yeah, in particular, so this S and T is not an issue for us because um, the vertex S will be the start state for the DFA and T will be the final state for the DFA. The issue in the conversion is um, at what all potential places can it violate the property of a DFA, because um, it's a it's not non-deterministic, right? So from every vertex there's only there can be at most two edges that go out of it. So if the graph G has like multiple, so many neighbors, then we might want to, okay, so you have an instance. Okay, let me just draw this on the new page. So you have the reachability instance, which is G comma S comma T. We want to reduce it to EDFA, which is just a, yeah, just a DFA or a graph. So yeah, so the point is if let's say S here has several neighbors, okay, let's say it has four neighbors, whatever, okay, then we might want to change it so that I mean the structure corresponds to the DFA, right? You can only have two neighbors at most. So Mm, yeah, so what you will have to do is something like this. So let me name this A1, A2, A3, A4. Um, One way to do to carry out this is that maybe from S you go to, you'll have to branch out like this, add some dummy vertices B1, B2, and maybe B1 goes to A1, A2, and B2 goes to A3, A4. So you will have to branch out. If there are, sorry, if there are more neighbors, then you introduce a middle layer, which is um, yeah, so S goes to B1, B2, and then you branch out these two further. Okay.
So, but quite possible that the dummy states introduced here. I mean, in the graph, quite possible that these vertices may lead to a path to the target.
Yeah,
And
that.
so, but then can we do one thing that without the loss of the generality, we assume that the sigma for the DFA, alphabet for the DFA is at least as large as the maximum degree of the graph is. That will not
Mm,
affect the this entire reduction in any
no,
way. Okay.
no, that is a very strong assumption to make. In fact, this entire conversion. Mm, yeah, so I was assuming that we have a binary alphabet here, because of which we have to take care of all this. But if you, yeah, if your, yeah, if your sigma is um,
What do I think of dummy vertices?
yeah, okay, just give me a second, okay, let me complete this thought. So um okay, yeah, if you think of sigma as the size of sigma is the maximum degree in G, yeah, then you are already done, because yeah, because then you can justify these parts. Yeah, that is correct. So then you don't even need to do all this. Agreed. And yeah, yeah, you're right. So you don't need to make sigma binary, because DFA is something that we are giving. Um, we are giving. So we have a choice of sigma. Yeah, you are right. So Q sigma S. Yeah. So we don't really need any of this. So I'll just take this some, yeah, on the other page. Hmm. Yeah, good.
And now this transformation seems straightforward
So
because I mean this
yeah,
now we can use this algorithm. Non-deterministically, we make a jump from a state to the other state. It's like that as if we are making a jump from a state to the other state. And now this entire correspondence can be done in the not more than logarithmic amount of the space because we would only be storing the values of the counters. That makes sense now, yeah.
yeah. Yeah, but just out of curiosity, if let's say I were to, for some reason, if I were to make sigma binary and I do the previous thing, yeah, that you introduce some dummy states here, you are not, I mean, you are still preserving reachabilities, in the sense that if you could reach from S to A1, uh, then you are still able to, the path is still there. If there was a path in the previous graph, the path is still there in the new graph, it's just that it's a bit longer. And if there were no path from, say, u to v in the previous graph, you cannot suddenly add new paths, right? So by this operation has a name, right? So um, it's called subdivision. Yeah. So let's say you have u to v edge, okay, and you introduce a new vertex here, such that u to a is an edge and a to v is an edge. So this is called subdividing the edge UV. So this is like a dummy vertex. Okay, so the property that this operation has is that by subdividing a graph like this, okay, you just look at any edges, you keep on subdividing as many times as you want. The property is that in the original graph, if there were a path from some S to T, there will still be a path from S to T. It may be a different path, but there is a path from S to T, and if the previous graph did not have, then this graph will also not have. So um, it does preserve, but whether it will be a logarithmic reduction or not, that's something not easy to say. So, yeah, are there any questions about anything that we discussed so far?
No, no, it's clear. Yeah, it's clear now.
Yeah. Saurav, you had some question, I think.
What do you think of dummy vertices?
Um, Basically, we just want to preserve the paths, right? So if um, yeah, so let's say u and v is an original path in the graph. You want to still preserve that graph, but you want to reduce the degree. So these dummy vertices are just some vertices that were not in the original graph G, but we added them into G prime to reduce the degrees while still preserving the reachabilities with respect to the original vertices.
Okay, I can understand what you say.
Okay. Uh, okay, good. So any other questions? Okay. Um, yeah.
So, given a directed graph, testing if there is a cycle is in NL. So, yes, that can be done. This is in NL. I just need to keep on storing the counters non-deterministically, keep on moving uh, to the vertices, and then if I can reach to the same vertex, then this will show the significance of cycle. And given an undirected graph, testing if it is bipartite or not is in NL. So in the bipartite graph, probably there is a cycle of the length 2. I don't remember. There is one characteristic of the bipartite graph and cycle. So do we have cycle of the length 2? Is this the characteristic? If
Yeah, so the property is that graph is bipartite if and only if it does not have an odd length cycle.
oh, I see. Yes.
Yeah,
So
because
yeah. So since cycleness can be done in NL, so yeah, this can be done in NL. And given a circuit, testing if it is satisfiable is in NL. So for the circuit thing, like say circuit is same as satisfiability problem, and satisfiability would require the space of order of n at least, cannot be done in the log n thing. So out of these three, A and B are correct, and C is not correct.
okay, I mean, it's not that C is not correct because otherwise,
I think A and B correct because A is true because directed cycle detection can be done using reachability, and number two, we can guess a path and check if we return to the same node. So and statement two is true because bipartite testing is in P polynomial place, and C number two, it since P subset of a NL it is also in NL.
Uh, Sorry. Okay, so a pun comment about B is that so if bipartite checking can be done in polynomial time, but P is not. I mean, we don't know whether P is sorry, we don't know whether P is contained in NL, right? So this is something we don't know. So even if bipartite checking is in P, it does not imply that uh, it can be done in non. I mean NL. Um, I mean, is this okay?
Yes, yes, I
Okay,
think
so
I may mistake something.
yeah, so yeah, it's okay. So what I mean to say is just showing that something is in P will not imply that it's in NL. And for the third thing, for the yeah, so given a formula phi, check if it is satisfiable. This is nothing but your three sat or satisfiability problem. Okay, so this is nothing but your SAT problem. We know that SAT is NP complete, SAT is in NP. Okay, so if SAT is in NL, this would imply that um, NP is okay. So, okay, maybe this is not directly true, but yeah, if SAT is not in NL, this would definitely imply that NP is not equal to NL. Because there is a language which is in NP but it is not in NL, so that would be enough to separate the two. The other way around, sorry, this is L. So the other way around, I'm not sure. It depends on whether all languages in NP reduce to SAT in logarithmic space. Okay, so yeah, so other yeah, I mean, is that clear? So if SAT is in NL, then can we say that NP is equal to NL? So is this do you see the problem with this making such a statement?
So if set is the element of NL, that would mean that something which is running in the exponential time is requiring logarithmic space. So that is,
Polynomial time and logarithmic space. Yeah.
yeah. So that cannot be correct. That cannot be correct. That cannot be correct in the sense set is taking exponential time with the deterministic machine. But NL would mean that this is decidable in the logarithmic space, but then using by NTM. So if I take the definition that set is in NP, so set is decidable by the NTM in the polynomial time. So polynomial time and logarithmic space seems justifiable. So, but uh, so I mean, just because one problem is there in NL, so all those problems which are there in NP are at least as hard as the satisfiability problem is. So if that NP complete problem itself belongs to NL, then that would imply that yes, NP is equal to, I mean, all those problems can also be solved, would also belong to NL. And that would mean that NP is, so if set is the element of NL, then NP would be the subset of the NL. Not
Yeah. So, um, yeah. So if SAT is in NL, that means for every language A in NP, we know that A reduces to SAT. If we could show that this reduction works in logarithmic space, suppose that every language A in NP reduces to SAT in logarithmic space. Furthermore, SAT reduces to reach Yeah, okay. So, okay, what am I trying to say? Yeah, sorry, we don't need a reduction further. Furthermore, furthermore, SAT is in NL. So this would imply that A is also in N A is also in NL, because I take my problem, I use logarithmic amount of space on the tape and I convert it into a satisfiability instance. Now I solve that satisfiability instance within logarithmic space because SAT is in NL. So I would have solved A itself in NL, right? So if such a reduction exists, then SAT is in NL would imply that the entirety of NP is contained inside NL. And this is a problem we don't know, as we mentioned earlier, right? We don't know whether um, L is equal to P, we don't know whether NL is equal to NP. So none of that is known. So therefore, the answer to C is not that it's not true, it's that, I mean, we don't know whether it is true. But yeah, but is are these two things clear? If not, then yeah, I mean we can discuss again.
No, no, this is clear.
Hmm. Okay.
This is clear, except that. But my query here is that Savage theorem says that P space is equal to NP space, or uh, D space is equal to N space. So why don't we apply the Savage's theorem to the L and NL and show that L is equal to NL? It's just the only issue because the Savage's theorem is applicable for wherein the function fn is greater than or equals to log n, or function fn is greater than or equals to n.
Yeah, yeah,
There is there any other reason for that?
yeah. That's the only reason why we can't, yeah, use Savage's theorem to show, to conclude L versus NL.
And why do we require that inequality, by the way? Because the in the proof of the Savage's theorem, they use just divide and conquer and the recursion. So even if we assume that fn is very well, I mean maybe equal to the log n as well, then also the Savage's theorem would be applicable. So why to make this assumption that fn should be greater than or equals to log n?
Okay. Um. Okay. Let me just finish off A and B, and we'll come back to the discussion. Is that okay?
Sure, sure, sure.
Okay. So yeah, I mean, I mean, is it clear to everyone that, I mean, C is something we don't know whether that's true. And for A, yeah, as both of you said, A is in yeah, checking whether, given a graph G, check if there's a cycle. Okay, so what you will do is, you can check whether there is a, let's say, v1 to vn, these are the set of vertices in G. Then basically you are checking whether there is a v1 to v1 path um, um, in G. This is nothing but a reachability problem. You can do this in NL. If you get a path, then you say that G contains a cycle. If not, then you do the same thing for V2, and you are reusing space here. Once you have that answer to this is no, just reset the space and use that same space again. This can again be done in NL, and you keep on doing this. If in the end Vn to Vn also there's no path, then you say that G does not contain a cycle. So this entire thing can be done in NL. Okay, good. So for the other thing, if you want to check that, if you want to check whether given graph G is bipartite. Okay, so one property or one fact slash theorem about bipartite graphs is that a graph G is bipartite if and only if G contains an odd cycle. Okay, so one direction of this is easy to see. Um, if um, if let's say G contains an odd cycle, then what will happen is, let's say you put this thing into the into the green partition, then both of its neighbors must be in different partitions because you cannot have edges within the same partitions. Then therefore this neighbor of blue must be green, but by the same idea this neighbor of blue must also be green. It should be in a different partition, but now you have that these two are in the same part, I mean these two have an edge, which should not happen. So no matter how you two color this, you will end up violating the bipartiteness condition. So the reverse direction is easy to see. The forward direction just needs some more work, but yeah, we will not prove this theorem. We will assume this theorem and show that checking bipartiteness is in NL. So now what you do is, earlier you were only checking for each vertex whether v1 to v1 there is a cycle. Now you also look at the length because you want to make sure that there is no odd cycle. So from vertex v1, check if there is a cycle of length 1. So v1 to v1, a path of length 1. Sorry, that's not even possible. Yeah, v1 to v1, check if there is a cycle of length 3. If there is um, if there is a cycle, then you will say that no, the graph is not bipartite. Cycle exists implies no, G is not bipartite. Okay, otherwise if this is no, then what you do is you check if there is a cycle of length 5. So from v1 to v1, check if there's a cycle of length 5. Again, the conditions remain the same. If you get a cycle, then the graph cannot be bipartite, and you keep on doing this. Let's assume that n is odd. Keep on doing this n by 2 times, or yeah, even smaller than that. So yeah, I mean you repeat the same process for each vertex. So the vertices thing is just using the graph, but reusing the space. But observe that this does not blow up the space, because even if you keep a counter, it's still logarithmic. I mean, even if you are storing this extra information, you are storing the vertex, which vertex you are currently at, and you are storing the length of the cycle. So this is logarithmic space, this is logarithmic space, and then further you are just using the reachability algorithm for checking existence of cycle. So that is another logarithmic space. So totally it's still logarithmic, and then you are just, when you repeat for v2 and so on, you are just reusing that space. So all of this can be done in NL. So is this okay?
Yes, yes.
Okay, yeah. So now we'll come back to your Savage's argument. So n space of log n okay. Okay, so okay, so you have this Okay, yeah. So just to repeat whatever I mean, the main idea. So this is the theorem that we have. So if you're talking about NP space, then you have n to the c space, and what I can do is, if I want to convert that machine into deterministic one, I will end up doing a blow up by quadratic. So if I try to convert this into deterministic machine, I'll end up using dp space of n to the c whole square, which is still polynomial. Okay, this is still order n to the c. So therefore by this argument you get that np space is equal to p space. Okay, because polynomial amount of non-deterministic space uh, can still sorry yeah can still be simulated by a deterministic machine with polynomial space. So this is a nice um, um consequence of the Savage's theorem, but this does not solve the this does not solve the NL versus L problem, because if you do a quadratic blow up of this, you would um, yeah I mean, log n is asymptotically smaller than log square n. If you are with higher space, this constants are subsumed, but the in terms of asymptotics, these are separate. And to answer your um, question, so why why did this happen, right? So the idea, as you mentioned, is a simple, nice divide and conquer idea. You have to check whether there's a path from S to T in the directed graph. So what you do is, you say that, okay, if there is a path from S to T of length 2 to the k, then there must be a vertex u which falls exactly in the middle. Okay, so there must be a path of length 2 to the k minus 1 from S to some u, and there must be a path of length 2 to the k minus 1 from u to t. Right. So yeah, so now you want to check whether you want to check reachability from S to U, and you have to check reachability from U to T. So what you have done is, um, you have reduced the length of your path from 2 to the k to 2 to the k minus 1, which is, you have halved the number of path. Now you can do this thing recursively. So you'll ask, so okay, if there is a path from S to U, then there must be a path from um, S to V of length 2 to the k minus 2, from V to U of length 2 to the k minus 2, and you can keep on doing this, keep on reducing your sub problem um, over and over again, until you finally have made it trivial and it's just a matter of checking an edge or something. So so what is the complexity of this um, of this algorithm? Okay, so this entire um, okay, yeah, so one thing is that you have, if you have the length of the path is 2 to the k, then you are halving it each time. Okay, then you'll end up having logarithmic number of steps before you reach a um, trivial instance, right? So if you keep on having, you'll have order log n steps before you reach a trivial size, right?
Not log n, but like say 2 raised to the power k here. So we will be requiring of the order of log 2 raised to the power k.
Yeah, but what what is 2 to the k? What is the worst possible length you can have? You can have a path of length n minus 1.
Yes, in that sense, yeah.
So log of n minus 1 would be, yeah, roughly order log n. Yeah. And yeah.
No, I mean, not this of the order of log n amount of the steps, of the order of log of 2 raised to the power k. And this log of 2 raised to the power k becomes more or less equals to of the order of k number of the steps. And yeah, so this log n is not appropriate, I guess.
So the number of 2 to the k is at most n minus
So
1.
that in that sense, yeah, fine.
Yeah. So you would end up taking at most order log n steps. Now the other thing that comes here is that you are actually, because in, I mean, if you were allowed non-determinism, you are guessing from s. Okay, where do I go next? Okay, you are just guessing. But if I don't allow you that power of guessing, then you are left with no choice. I mean, in terms of deterministic simulation, if you want to do it this way, you will have to go through all of them. Okay, so here you don't have the power of non-determinism to guess what is the middle vertex. You will have to go through all of them. And the good thing is that you are allowed to reuse space. So maybe you take the vertex u to be the first vertex, let's say v1, and check whether this is true. And let's say that is not true, then you do for v2, then you do for v3, similar to what we were doing here earlier, right? We don't know what that correct vertex is, so we did for all of them. So similarly here, it's a there exists u thing, so you have to do for all vertices u in v and check if the condition is true for at least one of them. So then you need some memory to store what is the current vertex that I am simulating right now. So this will take further log n space to remember this, keep track of this counter. So order log n into order log n, this will um, yeah, this will come out as order log square n roughly. I mean, it's a recursion that we need to solve, right? Every time take your instance of len 2 to the k, and you are converting it into log n instances of half the size. And you, there's some analysis that needs to be done. It's not, yeah, it's not obvious from the yeah, I mean from the logic. So you need to write the recurrence and solve it, and you end up getting this order log square n thing. So um, yeah, so the fact that this blow up happened is because of two things. One is that we had to guess this u, and second is that we had to solve for the sub problems recursively. So if yeah, it's not clear why we'll be able to save space if yeah, I mean, you have logarithmic amount of space to work with initially. So I don't know if that answers your question, but
But in the Savage's theorem, I did not see the statement like the. Uh, can you scroll up this slide? So can you scroll it up this slide? So wherein you wrote the statement of, yeah, n space of log n and is a subset of the d space of log square of n. Instead, I read the statement like n space of fn is a subset of the d space of fn square.
yeah.
But
So yeah, so that is a general that's a sorry, that's a general theorem. So the n space of fn is contained in d space of um, fn square, where for all fn at least log n or something, right?
yes,
Okay.
and so is this statement also true that n space of log n is contained in the d space of log square of n? Is this also true, or you wrote this for some other purpose?
Yeah, so if you just take fn to be log n, then I mean substitute fn to be log n, then you would get this.
Is this true or not true?
Yeah, this is true. Yeah, this is a special case of the theorem, right? If you just take fn to be log n.
Oh, I see. So then why don't we have NL is equal to L then? Why
Yeah,
so?
because what this tells you is that NL is contained in d space of log square n, but L is the set of languages that run in order log n time, right? So, and you know that log square n is asymptotically larger than a log n.
Yes, now I understood. Yeah, thanks. I have understood this.
Yeah,
Thank you so much. Yeah.
yeah. Hmm. Yeah, are there any other questions about any of, yeah, whatever we discussed? So, okay, good. So, maybe, yeah, let's do just one more question. So you are given some statements. So first statement is L and NL are both are closed under complementation. So is that true?
So L and uh, decided. So if L is decidable, then can I decide the complement of L as well, and with the machine, and that is so P is closed under complementation for sure. And if P is closed under complementation, then can I use the same thing for L and NL as well, on the basis that L and NL both are the subset of this thing?
No.
But that is not applicable
Yeah.
because BCFL is closed under complementation, but the normal CFL is not. Yeah, so that is not the criteria.
Yeah.
So
Yeah.
uh,
Closure does not yeah, flow for subsets or supersets. Yeah. So
yes.
maybe let's do L first. So L is easier. So if
I think all the statement are true because first statement is true because L is closed under complement and NL is also closed under complement uh, due to L equal to COL and NL equal to CONL
yeah,
and
so
statement.
uh, yeah. So let's say by L is equal to coel. So coel is the complement. Okay, so maybe let me just say that if A is in L, then you want to show that A complement is in coel, or yeah, basically you can, yeah, A complement is in L. That's it. So how would you show this? That's the first question.
So, like the Immerman's theorem says that NL is equal to co-NL.
Correct. So yeah. So what's the spelling? Sorry, I may not be correct on the. Yeah, maybe let me just write. It says that NL is equal to co-NL. So therefore, NL is closed under complementation. Yeah, good. So this is fine. Mm.
Now the thing is that as far as the L is concerned, so if A is the element of the L, then I don't know.
So how would you show that if A is in P, then A complement is in P?
Yes. So if A is in P, then I just need to flip the yes with the no and no's with the
Yeah.
yes.
So can you do
Really?
the same thing for
I
this
wish
one?
I'm planning to do the same thing here, and probably that can be done. Yeah.
Yeah, because you run your machine, the same algorithm. Okay, so let's say A is in L via machine M, and the new machine M prime basically run M on X. If M accepts, then you reject, then reject, and if M rejects, then you accept. This is what M prime does. And what is the language of M prime? The language of M prime is the complement of A. And what is the space that M prime uses? It takes log space for running M on X, and then this is just a 1-bit flip that we are doing. So this machine runs in logarithmic space. Okay, so therefore A complement is in L. Same idea, but we don't know whether NP is equal to co-NP. Okay,
Right.
so
And
yeah.
this co thing is true for the BPP as well. That BPP is equal to co-BPP. So is there something a criteria or something known that in which scenarios a complexity class becomes equals to its co-complexity class, and in some cases it does not.
No, so we don't know such a characterization. In fact, yeah, yeah.
Okay, okay, all right, yeah. And for the second part of this question, you have already answered. The Savage's theorem solves reachability in of the order of log square n space, because this reachability is the element of NL, and if NL solves of the order of log n, so that is the D space of log square n. And if that is the case, then this polynomial, this space is log square, so the time would be polynomial. So B is also true.
Uh, so you are right about the first part, that yeah, by Savage's theorem you are actually solving this in order log square n space. That is fine, but is the time still polynomial?
So, like say, if so, that would be 2 raised to the power log n square, and 2 raised to the power log n square would be what? 2 into 2. We came out to the polynomial space only, or what?
Yeah, so you have order log n space, so time would be 2 to the
Log n
let's say k
log,
logs. Yeah, let me just take k is 1, log square n time. This is 2 to the log n to the log n, which is like n to the c to the log n. This is quasi polynomial. uh, this is not bounded by any constant,
right.
right? So this is more than polynomial, this is quasi polynomial time. Okay. Hmm. So this is not correct. Okay. What about the c?
So, using DFS, one can solve reachability in polynomial space. So, yes, so if I yes, time could be exponential, but since the space is required, and polynomial time. So S to T, yes, whether I can make a move from S to T. This is true. This is true. We use we often employ DFS for this thing, to solve the reachability, to identify the loops, etc. So polynomial time is required. If time itself is polynomial, the space cannot exceed time. So this is true.
Correct. So yeah. So DFS does run in polytime, so the space is automatically bounded by polynomial. Yeah. So this is in fact a nice, you know, trade-off. If you use DFS, you are running in polynomial time, but the space is also polynomial. But if you do a Savage's implementation, you are saving on space. So from polyspace you are going all the way down to log square n space, but then you are doing bad in terms of time, so this poly will actually become n to the log n. So that, I mean, yeah, so you are compromising on time there. Yeah, so any other questions? And yeah, is there anything that you were pointing out that time, Sora?
No, 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 no. I have no doubt.
Okay. um, okay, then that is all for today. Yeah. Okay, I'll stop the recording.